I'm really excited. This is my first time at Data Council and have a lot of really interesting topics to go cover with everybody. So let's get started. We're going to talk about smart orchestration. Have a whole host of things that we're going to go touch on here. We're really going to spend most of our time talking about why pipelines suck and how we could go build a really cool new control plane that makes life a lot easier. So if you build data pipelines, if you've done this for a while, this will probably make a lot of sense and be a really interesting topic for you. Quick little bit of introduction. Ascend.io, one of the sponsors here. We have a booth back there. We are a 4-year-old company, roughly 30 folks, mostly engineering. Been building our product and technology for 4 years now, and the TLDR on us is we absolutely love data pipelines. We have a long background experience building them. For myself, I've been building data pipelines for about 15 years now. I started my career back at Google way back when as a software engineer on front end. Thought I was going to be doing all of this great front end code and quickly found myself writing more MapReduce jobs, analyzing our results than I actually did front end engineering. I've really spent the last 15 years then building out companies and teams and products in and around data and engineering. One of the really interesting things that hopefully captures some folks' attention here is at Ascend, one of the really exciting scale moments we hit a while back was the ability to actually process over 1 trillion records flying through our system in a single day. And it's funny because size and scale usually catches people's attention, but I think there's something far more interesting than just pushing large numbers of records and bits and bytes through the system. And we're going to talk about that a little bit. Because in the process of doing that, it was also hundreds of thousands of Spark jobs that were all intelligently and automatically orchestrated. And that's going to be one of the really interesting themes to cover here today. Quick bit about Ascend, just to give you a little bit more context around the technology we're talking about and where it sits in our tech stack. Our whole fundamental belief is that we should be able to build smarter pipelines in less code. Sounds fantastic. Really where we spend a lot of our time and where we're going to talk today is the system that underpins a lot of this, the core technology, that orchestration layer that makes it so that we can write pipelines to connect any data source, any format, any transformations, and feed it into other systems. And so we're going to spend a lot of time around how do we create that highly intelligent control plane that can do really smart things for us and with our data. All right, so on to a little bit more of the meat. Despite the advancements that we've seen and that I've certainly seen in pretty much every part of the data lifecycle, building pipelines still kind of sucks. It's funny, over the last 15 years, I've watched a lot of the industry evolve. I've written used all the early versions of Hadoop to Spark to Storm, have used many of the technologies on this slide and many others that have simply died off. But it's been really interesting when we think about the maturity of our data ecosystem today. There's a lot of really powerful technologies out there, right? We can process more data faster at larger scale, do really advanced things with our data. Yet, as data engineers, as we create all these pipelines that fuel all of this great downstream innovation, we're still stuck spending the vast majority of our time up here. And this I found really frustrating over the course of the last decade as I was building and using a lot of this technology. And so, really the core goal that we've set out to solve is how do we make that part easier? And to do that, you really have to explore, why do pipelines suck? Back in the day when we could fit everything inside of a database, inside of a data warehouse, life was really easy, right? Like you jam a bunch of data in, you write a few lines of SQL, and it gets pumped through the millions of lines of brilliant code that the database engineers wrote, and you get your results. And that was actually pretty cool and simple. When we start to think about data pipelines, however, we're no longer pulling data out of a warehouse. We no longer have a database engine, a query planner, a query optimizer that does a lot of our job for us and makes life easier. When we start to move to data pipelines, we're now pushing data through. And it introduces a whole host of new challenges that we have to go solve for. We have to figure out, how do we look and watch for new data? What format does it sit in? How do we profile and partition that data, because we need that information to figure out where we push it next? The short version of this is every stage of every data pipeline that we create, we're essentially re-implementing query planner and optimization heuristics. We're just pushing stuff through as opposed to pulling it out. And this part, to me, when we started Ascend 4 years ago, just seemed absolutely crazy. Like it seems like we're solving the same problem over and over and over again, and we should be able to tackle this once and for all. So when we looked at a lot of the ecosystem today, and I'm guessing most folks around the room here have worked with some of these technologies, and I certainly have worked with most of them. When we looked at the evolution of the ecosystem, we've seen a few moves, right? We've seen from the sort of cron, Uzi, Luigi, and now Airflow era, we've seen the move towards SaaS offerings, more templatized, augmenting pure code-based with GUI-based technology as we move to some of the SaaS vendors. But what we've also seen is nothing has really moved around the design of the control system itself or the programming model. We're still using schedulers that are based off of timers and triggers and are very task-centric. And we're still following an imperative engineering model. So hang on, there's a few of these in there. We started to look around for ideas in adjacent spaces because we can't be the only ones trying to solve this problem or dealing with these category of challenges. So quick few surveys here for the audience. How many people here have used databases? It's a really easy one. All right, whew. How many people here have heard of React? Awesome. People use it on a regular basis? I'm guessing for a data engineering group, probably a smaller group. Yep, cool. What about Kubernetes? Kate's fans? People use it? People heard of it? Yeah, awesome. What do they all have in common? They're declarative. They all leverage declarative programming paradigms and apply it with a control flow or a control plane to automate a lot of the underpinnings of that challenge. So when we think about declarative programming, it's a programming paradigm that allows us to express logic that describes the flow as opposed to actually implementing it. It allows us to eliminate, or at least minimize, a lot of the side effects and allow the program to actually optimize on our behalf. Simply put, it allows us to describe the what as opposed to the how. And we've seen this move across a number of different domains over the course of time. So let's think a little bit more about these trade-offs. Declarative. Promise you there's going to be some more. Declarative and what we really want to go after is ultimately the desired outcome, right? They're Simpsons fans. Homer loves his beer. That's what he wants, beer. You get two different approaches, the what or the how. In the declarative model, he can describe what he wants. In the imperative model, he's got to go figure out how to brew his own. What we have found over the course of time is that this generally leads to different outcomes, regardless of the desired state. I've spent many, many, many nights, weekends, and days on the right there, incredibly frustrated with trying to build and maintain and optimize my data pipelines. Others? All right, yeah, there we go. So let's get a little bit more specific. Trade-offs between declarative and imperative. Then we're going to dive into how we do that. Declarative systems. The pros are really pretty stark, right? They are less code, faster dev cycles. They can be far more adaptive to changes in the environment. And ultimately, they provide less maintenance burden for us. One of the reasons why they're so hard and why we don't see as many of them, however, is they're domain specific. They actually require a context and understanding of that particular domain. In this case, data pipelines, which means they're incredibly hard to build. They also can be difficult to manually optimize. They're highly automated systems, and as a result, oftentimes don't give way to really custom tuning and that high degree of flexibility. Conversely, when we look at imperative, the reason that we see most technologies when first introduced into new domains be imperative is they're simpler to introduce. You get incredibly high degrees of flexibility, incredibly high degrees of control. The challenge that you get, however, is you have to maintain state. And as a result, you end up having a lot more complexity inside of your imperative-based systems because of this need for state. You have to do things like track that and determine, based on current state, what task must come next. It means that a lot of your code and your assumptions baked into your code are stale the moment you ship them. They're from a snapshot in time, as opposed to having to a system that can adapt to those new understandings of the environment. So, put a different way, a great quote by our CTO, Stephen Parks, who's right down here, is imperative gives you the ability to do anything, yet it also gives you the responsibility to do everything. And that's the fundamental trade-off. Ease of use and speed versus flexibility and control. So let's talk about building of a declarative control plane for data pipelines. South Park fans? Anybody know the underpant gnomes? Yes, all right. This is how we started. We basically started our journey with this master plan, which was we need to do something around declarative pipelines, and there's going to be something really big in the middle. We're not sure what yet, but ultimately we should profit. So we spent a lot of time thinking about what should a good control system do for data pipelines. And we came up with a massive list of things to do. For those of you who have built data pipelines and data systems in the past, probably have a lot of features and functions like this. A lot of these are the things that we only have to do because we don't get a database engine, because we don't get a query planner and query optimizer. These are essentially the core features and functions of what a pipeline engine would look like. So then we spent what we thought was going to be 1 year, then 2 years, and then 3 years building this. And we actually launched our company out of stealth about 4 months ago, really having built out a lot of this technology and backed by the sort of core backbone of this control plane. But let's spend time now talking about how does this actually work? Core design and architectural principle as you create a declarative system that's fueled by a control plane is you have to have separation of logic and control. You need a higher level blueprint that is your logic plane, and your control plane is the system that understands that and dynamically generates the tasks to derive a new state itself. So we're going to spend most of our time really focused on that control plane. When we think about the control plane system must be able to answer the following questions. First, is there anything I need to do? That's really based off of the answers to the following ones, which is, what is the current state of my world? A job of a dynamic control plane is to take you from one state to another. And as a result, you must know where you stand to be able to generate any possible task that could take you to another state. Simple enough. Third, what should my state be? Followed by what doesn't match. Right? A good control system is doing this many, many times a second across many, many, many elements. And then ultimately, how do I fix it? So let's dive into a little bit more depth around how we accomplish this for data pipelines. For those of you who have built data pipelines in the past, let's think about, is there anything I need to do? And take a really simple analytics pipeline as an illustration. We've designed a lot of these. We've probably written them up on whiteboards in the past, and they usually look something like this, which is, I have a bunch of files that are sitting in somewhere, a blob store most likely, let's call it S3. They are sitting on this path. Here's some creds to go find them, and they probably have this schema. It could be one file a day. It could be one file a second. It could be thousands of records or billions of records. It shouldn't really matter. There's data. It's sitting on this path. Let's do something with it. The second piece is, what am I doing with data, right? So let's say I'm doing a classic sort of cleaning, enriching, and then analyzing pipeline. I'm probably doing some filters, some joins, some enrichment, and then feeding it into some sort of a transformation that's compressing the volume of data down into something I could then go put inside of a database, aggregating on different dimensions of users, compressing it down, and doing counts and various other aggregations by hour, day, week, you name it. And I'm trying to make sure that that database is, or that data set is actually properly synchronized with the database. All purely at a logic layer, has not yet actually been applied to data. Then we get into some of the interesting stuff, which is that second question. What is the current state of my world? What I did is over the weekend, I actually listed out some of the underlying bucket. In this case, it's Google Cloud Storage. And I listed out the files that were in my bucket. And there's tons and tons and tons of them. But what's really interesting is when I think about what's there, it's kind of hard to make sense of, right? It's basically my bucket, some UUID, and then some part files. But the magic is really what do we track with that notion of a UUID, as that starts to link in our entire understanding of state. That UUID is a fragment's UUID. With that individual fragment, with every single piece of data, a control plane needs to have a bunch of information about it. There's things like the data SHA, which is really easy, but not the most helpful thing you're going to track. Some of the more interesting things that we track that are incredibly helpful are things like the data profile. What's the min, the max, the cardinality of every single column? What does it span? This helps us infer what could be downstream calculations that would depend on that over time. Things like job statistics. What generated this piece of data? What files fed into this piece of data? What were the Spark parameters that we ran to actually process this piece of data? When did we do it? How long did it take? How much memory? How many CPUs? You name it. All of those statistics. This helps us have a lot of context around this piece of data. But then the really important part that we have is this notion of a PSHA. And this is actually one of the most key elements in creating a declarative system in the control plane is being able to track this PSHA. It's a special kind of SHA, and we're going to spend a lot of time talking about SHAs. The PSHA is a unique SHA, not just of the data, but essentially the journey of how that data arrived at the state in the system. So if we think about it, for source data, think of a PSHA as just the DSHA. It's a unique fingerprint itself. But the PSHA, when we get to downstream derived data sets, is a combination. It is SHAs of SHAs. For example, we actually SHA the transform, the code itself that generated that piece of data. It gives us a unique fingerprint to say, if this piece of code changes, if this transformation changes, we know then as a result that the data set itself should and needs to change. We also then SHA with that all of the input SHAs, the P-SHAs of the inputs itself, and recursively traverse back up the graph. There's a lot there in a single formula, and yes, it is my pseudocode. But this is the basic gist of it, is if any of the upstream data changes, if an originating piece of data changes, its DSHA changes and the SHAs downstream from it will change. If a transform, if the logic I'm applying to a piece of data changes, its SHA will change and its downstream calculations will also change. And so in the simplest form, this allows us to very quickly and easily say, should this piece of data still be here? What is its unique fingerprint? And it allows us to do it without actually having to look at the data itself. We can simply look at the originating data and the transforms applied to that piece of data. This allows us to short circuit a lot of processes around having to actually apply transforms just to see if the data has changed or not. So we're going to spend some more time on this in a bit, but the PSHA is incredibly important. So moving on to question number 3. What should it be? What should my current state be? From question number 2, we started from the bottoms up. We looked at all of the data and said, what are the PSHAs, what are the fragments that I currently have in my system itself? Step 3 is, let me now look from the logic plane down and figure out what do I expect and create a second set. So for that, we enumerate through all the various components and the transformations people have created. We then look through all their various partitions and we start to analyze a bunch of things. We analyze the transforms. If it's SQL, is it a map? Is it a reduction? Is it a partial reduction? If it's a PySpark transform, we look for hints from the user to tell us the same piece of information. This allows us to then determine what are the actual input partitions for this transform. From there, we can then load up the upstream, the profiles of the data from the upstream components themselves and look at their SHAs and figure out what those PSHAs are to generate our PSHAs. And we recursively traverse up, not just at a component level, but all the way down for each and every single partition of information. You'll probably get the sense too, this starts to become incredibly expensive computations over the course of time. So we'll spend a little bit of time later talking about how our scheduling system can do this multiple times a second across what could be hundreds of millions or even billions of partitions. So we'll talk about the performance things later. But the ultimate model for this is you end up generating a data set of things that are there and things that should be there. And then we start to look for what doesn't match. This becomes pretty clear and straightforward, right? As you're enumerating what you expect to be there, you're looking at its inputs. If the input for a component doesn't exist or its PSHA doesn't exist, then you need to queue it to get updated, to essentially be regenerated and repaired. If all your data exists, but your PSHA doesn't match, then you need to also queue yourself up for updating. It's a pretty simple step from there to just simply start to queue up the work to update PSHAs. And actually, I should say not even update PSHAs and generate new PSHAs and new fragments. And then the fifth is fixing. It's only at this step where we actually can start to generate work and say, well, I need to generate and update this new fragment that is aligned with this PSHA. What is the work required? I already know the transform. I can rewrite and optimize it. I know what the input partitions are. Let me go generate the work required to create this new PSHA. So we basically have all this information available. We analyze the input. We can consult a bunch of the statistics from previous runs and from the inputs themselves. And then we can generate the job. Pretty simple and straightforward from there. You also get the benefit of we can then start to monitor and watch for that job. And even when it's done, we commit it. And this gives you a lot of the ability to atomically commit at a metadata layer everything that has been processed. Now let's talk about how we scale this, because this is a really cool and really powerful system, but you also introduce a bunch of really interesting challenges. How do you traverse what could be 1 billion partitions that are generating and processing and trailing records every single day? And how do you actually run that loop and run that process in less than a second? So there's a few core tenets, especially as we scale that control plane. One of the things I mentioned was SHAs. We do lots and lots of SHAs. This allows us to short circuit having to actually look at the underlying data itself and or even generate jobs that may produce duplicate data. Everything gets a unique fingerprint, which makes the system really fast and efficient. Second, obviously, standard principle, cache. We cache everything. It gives us lots of performance gains. But this, when applied to a really unique approach, has given us some of the biggest gains of all, which is something we all learned in introductory computer science courses, which are trees are better than lists, well, more often than not. They're certainly more performant. But we create tree structures that are really interesting. We actually leverage the fact that our largest data sets also happen to be time series data. One of the few data sets that grows over time. And as a result, they have unique characteristics where we can load up that data and structure it in ways based off of our understanding of the data itself. This allows us to do things like aggregate all of the metadata. We know that if the data is coming in a year, month, day, hour partition structure, we can actually roll up and aggregate at each and every single node within the tree so we don't have to traverse that entire tree. Moreover, we can generate SHAs and persist the SHAs even at node levels, so we can rapidly assess has any SHA changed at any node in the tree. For example, has anything in the data set from 2008 changed? If that SHA itself hasn't changed, I don't even need to traverse any part of that tree as a result. So you get huge efficiencies there. The last one is be lazy. Our system has figured out how to not have to walk the entire data set, but instead start with high priority items and traverse until it's done. And the notion of done is not have I generated every piece of work that's required, but instead have I saturated the resources I have. We've added in the ability to monitor all of our underlying infrastructure. We know how many nodes, how big they'll autoscale to, how much memory, how much CPU, and we pair that with the resources we allocate for each and every single job. And as a result, we know when we've saturated the underlying infrastructure and can simply wait for a job to complete. This also helps give us the benefit of knowing if a task was completed, it may have new derived work once that task is completed, so we can simply wait and make sure that we're always processing the highest priority tasks. Now let's talk about the data plane. So scaling the data plane has also been really, really fun. One is do less work. So we do less work by doing a handful of things. One is we persist a ton of intermediate data, just as I think many of you have probably tried to do in your data pipelines. We are able to persist, which then pushes a lot of the burden back to storage as opposed to compute. Storage tends to be very, very cheap by comparison. And that persistence layer is really enabled by this PSHA calculation. The second thing that we do is we also deduplicate a ton of work. Remember, if I'm traversing all of the components in a graph that are being processed, at a certain level, I don't even know any longer what component it is. I just know that there must be a PSHA that exists somewhere. And so we get this really cool ability where, because I'm just simply looking up and figuring out, has a data set been generated that aligns with this PSHA, you get all this great added benefit of deduplication as a result. It's actually really hard to get the system to not deduplicate work as a result. The other thing is making sure you do the right kind of work. Spark, for example, is fantastic when it's dealing with a smaller number of really large files. It's not so good when it's dealing with a large number of really small files or just a large number of jobs in general. So we've invested a lot in doing things like small file aggregation, optimizing smaller jobs, and even have created our own specialized pools that are designed for things like smaller jobs. And then the last one, I talk about this in a couple more slides too, a little bit, is make sure you do it efficiently. We've built out a whole fabric that runs on Azure, AWS, or Google Cloud. We put everything on Kubernetes, and we try and leverage as many spot and preemptible instances as possible. We're almost to the point, hopefully soon, where we can do low priority VMs on Azure with our auto-scaled Spark in-case clusters as well. Then lots of cool little tricks like single zone clusters. One of the things we found, for example, is running multi-zone or multi-AZ clusters in Spark is really expensive as you start to shove data across availability zones. Even if it's fractions of a cent per gig, it really starts to add up. But in a world where these clusters can be rather ephemeral and actually move data around and pop up new clusters, this gave us huge performance gains and cost improvements as well. Now, SaaS-ifying it. We won't go into too much detail here, but everything that we've created, obviously, around this control plane, our entire tech stack is very heavily based on Kubernetes. Most of our services run either in Scala, which is all the things that basically touch data, tend to mostly be in Scala. A lot of our backend code is written in Go, which is really performant as well. And then on our front end, we are also Node and React fans. So a lot of these services have really been tuned. We talk gRPC, which has allowed us to actually be pretty language agnostic as to how our systems communicate with each other. And we do keep a pretty clean separation between that control and data plane as a result. Last few bits really fast. There's a whole lot of topics we didn't discuss. Garbage collection, the multi-cloud abstraction layer, how to do things like data repair, tons and tons and tons of other topics. As I mentioned, we've been at this for 4 years now, so there's a lot of stuff to discuss. Come ask me, come ask Steven or the rest of our team who's running around with some of the pipeline shirts. And we have office hours soon, 4th floor, room 476. Now, just bringing it back home really fast, TLDR, just to make sure that we recap this. The move from imperative to declarative in concept is pretty simple and straightforward, right? It's shifting the way we think about how we data engineer. It's moving away from the how, right? Imperative itself is I inspect state, I run tasks, and I generate data. And it's moving to declarative. The declarative model, simply put, is focusing on the what. I design logic, it's applied to data, and the tasks are simply a byproduct of that. This ultimately does allow us to create smarter pipelines and far less code. I think that's it. If you guys have questions, happy to answer them. We'll see you in office hours. We also have a booth out back in the back room where you guys can see a bunch of the technology at work as well. I think I hit my 30-minute mark. All right.